Okay, Habib Hocam, please.
Okay. Okay. Thank you, everybody. I am very much thankful to the organizer. They invited me almost a few days ago. So I didn't have chance to write my lecture on latex. So I just used my handwriting. I'm sorry. I hope you can read it. But this is how also I teach my students in regular semester. So I write them in advance and I produce PDF and then I go on. So if they have any question, I write in a separate paper. Anyway, so the title of this 1 hour lecture is Black Hole in Nonlinear Electrodynamics. So there are two concepts here joining, actually clashing. One is the concept of black hole from general relativity, and the other is the electrodynamic, but this time it's nonlinear version. So we all are familiar with electrodynamic from high school. We had optics, we had, I don't know, physics 1, 2, and then we came to university, we got electromagnetic actually. Then in our master time, electrodynamic, and then we had advanced electrodynamic and we came here. So we came from the concept of a point charge and its electric field and its direction and its magnitude and the Coulomb's law, and then slowly from the very beginning, I remember we had a problem. Our teacher in high school, they said, okay, look, the Coulomb's law is 1 over 4 pi epsilon 0 Q1 Q2 over R squared, but R cannot be 0. This is what they were adding to the comment, but nobody paid attention. Actually, they didn't know this is the most interesting part of the electrodynamics. Actually, that time we didn't call it electrodynamics. It was just physics. I don't know whether you had similar course in high school. But anyway, that R0, we ignored it, not only in high school, but also during our undergraduate. So nobody cared. Even a student, they were happy that R0 is excluded. So the teachers also, if you ask why R0 is excluded, they had no answer. So it's excluded. This is not a point you talk or you ask. So then we came further, but nobody tried to solve this problem. Still, R0 is excluded. I mean, when we look at the potential, again, potential is Q over R. So R0, what happens when R is 0? So then we use an advanced word for this point. We call it, this is a singularity, for a kind of pole for the space. So we try not to reach that point. But the problem is, okay, we said we have some rules, electrodynamic or electromagnetic rules. They were all discovered experimentally before Maxwell. Then Maxwell came and, you know, mathematically put them into few equations. And we know nowadays, one by one, we gave them name. So like the first one was related to electric field and the charge distribution, electric charge distribution. And then it went to the, we realized there is no magnetic monopole. So the second was about divergence B is 0. And then we went through the correlation between electric and magnetic through time. And 4 equations came out. We called them Maxwell's equation. And Maxwell also, from the mathematical symmetry of the problem, he discovered one of the equation needs additional term. It's a Maxwell addition to Maxwell equation. And then that displacement density, I mean. So then we combined the equations, we made wave equations, we solved them, we found, I mean, irrespective of the problem that was there, many things happened. And if you look at around, I mean, in your life, electromagnetic in the way we learn from high school to, let's say, even PhD time, everywhere. You look at light, it's, you know, it is described by the same electrodynamic. When you look at your mobile phone, when you look at TV, when you look at sun, when the heat comes to us, everything we see still without having interrupted by R0 works perfectly. It seems that Maxwell theory is perfect. And although R0, nobody solved it and nobody asked any question. But this is not the only. When you go dig little bit more, you will also realize, okay, we talk about in classical electrodynamic point charge. So let's say electron. So why electron, although it's just a point, but it has a constitution. So it has some part which may repel the other part. Why such kind of particle still is stable? So in addition to singularity, this is another problem. So then another stuff is when you find the total energy of the electromagnetic energy of a point charge is infinity. Another, it comes from the same point. Actually, R0 is a singular point. So from early 20th century, this was the question. These were actually the questions. What is happening to a point charge? Is it a misconcept? We should abandon such concept? Or there is some other theory which you should apply to this kind of, to remove this kind of problems. So this was actually the starting point that nonlinear electrodynamic came into agenda. So therefore, nonlinear electrodynamic, it is at the beginning, it is completely separated from black hole. So it's just like linear electrodynamic or Maxwell theory. You can cook it up and to see what is going on with the field, with the energy, etc. So such theory was given first by Born and Infeld in 1934. They decided to find a kind of, or invent a new theory. Actually, they call it new classical field theory. I would like to show you their first paper. This is their paper. I just downloaded to show you. So this is the first paper, and they called it Foundations of the New Theory. Yes, you don't see?
Yeah, we don't see it.
Oh, okay. So it means that I have to share. Understood. Okay, I know how to do it.
Okay.
I realize now. Okay. So actually, this is the paper.
Okay,
I think you see right now.
Yes. Yes, thank you.
Okay. So it was created in 1934, and as you see from the title of this paper, it's quite a very old paper, but it's written Foundation of New Field Theory. What they said new, actually they tried to remove singularity from the Maxwell theory, and also they tried to remove the infinite self-energy for point charge. So actually they were successful, and in making their theory, they were inspired very much from gravity, actually a special theory of relativity. So this is the Lagrangian that they have started with. As you can see, actually the more complicated version. So they have inspired by the action of gravity, actually, let's say, a particle in a special theory. So anyway, then they have created, they have actually made all necessary arrangement to make what they were, you know, supposed to do. Let me just go back to my lecture, 1 minute. So anyway, this is about nonlinear electrodynamic in from one side. And we have also black hole in other side. Black hole is a concept from gravity. So even Einstein's theory without matter in 4 dimension, it admits black hole, Schwarzschild. let's say, black hole. So black hole is a very interesting object coming as a result of general theory of relativity. And but we knew that combining gravity with Maxwell theory in the way that people they liked, they couldn't do, but they could manage couple them minimally. So in that minimally coupling between gravity and Maxwell theory, what came out, we call it a Rayleigh-Nordstrom black hole, or let's say call it Rayleigh-Nordstrom solution, because it may be black hole or a particle. So then the question is, okay, Rayleigh-Nordstrom black hole or Rayleigh-Nordstrom solution, particle solution, it has a lot of advantage, a lot of interesting aspect. People they have been working on since it was found. And now we're going to see if we combine or couple that gravity to the new, let's say, non-linear electrodynamic. What will happen? Will we have a solution which is richer than the simple Rayleigh-Nordstrom? What I mean richer, so Rayleigh-Nordstrom or short-sheet black hole, both of them are they are singular again. So we have a singularity at r equals 0. So that is another problem. So it means that the singularity of a charged particle, which was at r0, it was carried through the Rayleigh-Nordstrom solution through the energy momentum tensor. So since energy momentum tensor is also, as we know, the energy of the Maxwell's particle, so it brought the singularity into the Rayleigh-Nordstrom solution. So the question is it possible we introduce a kind of non-electrodynamic, not only cure the singularity inside, I mean, at the location of the charge, but also its total energy, and also the black hole become regular. So it's more understandable, and of course, singularity in the space and time, as long as they are singular in its general, let's say, meaning, is not welcome. So these are the things we're going to check in this black hole solution in non-linear electrodynamics. So let me just make it full screen that we can go on. So now what I'm going to do in the rest of the this 1 hour time I have, I introduce directly the action from gravity coupled with non-electrodynamic. And I have observed many new researchers. They came into this topic, which is very interesting. But the problem is, since they used the field equation directly from some papers, published paper, they made very trivial mistakes in just copying and pasting the field equation. So I decided for first time as a lecture, and I hope forever, for the last time I mean, I give all the detail of finding the field equations, which if anybody in this room, they would like to work on this theory, they know what equation exactly they should work on, and they will also see the process of finding the equation. So this is the first part, my stress on this lecture. And then I will give one example, which is actually, I could give many examples. We published papers on new models, but I decided to give the solution of Born-Infeld theory, which is very well known, and I think everybody should know how to find it. And finally, I will give you some general overview on the Lagrangian, which we will going to see in a moment, and the future. So now the thing here I wrote, these are what I already said. So non-electrodynamic, in addition to what I said, it also is applied to strong fields. So if you look at the particle, which I mentioned, the charged particle, really when you are far from particle, the Coulomb's law or the Coulomb field may be correct. So this is why everything we established so far based on Maxwell theory, they work perfectly because we are really far from those charges. But if you go very close to the source of electric charge, then in addition to having a small scale, the field also is very strong. So then it comes to our mind, is it possible we apply another theory over there, which is in distance gives the Maxwell theory, but when it is a very strong field, it behaves differently that such that the singularity goes away. And that is how this nonlinear theory is usually, they say, is generalizes Maxwell theory for strong fields. So that is one case. And I already said in 1934 it started, although before 1934, they were spelling questions, the question even we knew from high school. So then Born and Feld, they tried to remove the singularity from the charge and also from the energy of the particle. And also, at the moment which we are now working on nonlinear theory, there are other applications, especially in quantum electrodynamics. Quantum electrodynamics was created in the second half of 1930s, I mean 1936 and after. So in quantum electrodynamics, we see that, and the thing we call it photon-photon scattering or light-light scattering is possible. And then the procedure, or let's say we call it the mechanism, may be explained by a nonlinear electrodynamic. So these are the things that we nowadays interested in nonlinear electrodynamic. Of course, as I said, since it is one of our lecture, I don't go through each of these items in detail, but you can search on Google or literature to find more references and information. So now, as I promised, directly I start from the action, which gravity is coupled with a nonlinear electrodynamic model minimally. So now you see here, L, X, and Y is our nonlinear electrodynamic model. Actually, X and Y, they are just Maxwell's invariants. One is just F mu nu, or in other words, E squared minus B squared minus E squared is the energy density, if you remember from undergraduate. And Y is also the second invariant, F mu nu star. A star is the dual field of electromagnetic field. And if you just a little bit go back to the first course you took in special theory of relativity, you remember the Einstein itself was very much, inspired by electromagnetic, Maxwell theory, because after Maxwell's equation were written into the covariant form that we know nowadays, the symmetry of the theory and the thing we call it nowadays Lorentz symmetry of the Maxwell theory were very much obvious. And then the concept of four vectors came into the agenda. And especially when we talk about F mu nu, which is the electromagnetic tensor, we also should talk about for potential A mu, and also we have for energy density, or let's say for charge density. So these are the things they came to actually mutually from the Maxwell theory in the covariant form, and also from a special theory of relativity. So this F star, which we call it the dual of Maxwell field or electromagnetic field, are coming from there, and its definition is as you can see in this relation. Here, of course, our space-time is going to be curved. That's why here G, which is the determinant of our metric tensor, is not 1. So, but if it is 1, simply F mu nu star is just minus 1/2, 1/2, epsilon, this is Liouville symbol, F alpha beta. Anyway, so these are very well known, I think everybody knows. The only thing I would like to say is, here L is a function of X and Y both. But in Maxwell's linear theory, this L was just proportional to minus X. So it means that Y didn't appear in original Maxwell theory. Anyway,
can I ask a question here?
Yes, of course, sure.
Why? What is the motivation of weakly coupling? Weakly coupling.
Weakly coupling.
Minimally coupling. Sorry, not weak. Minimally coupling.
Oh, okay. Look, actually, as you can see here, our Maxwell theory, Maxwell Lagrangian L, let's call it. Actually, it is nonlinear Lagrangian. It interacts not directly with R, I mean with the space-time, but indirectly through G. You can see here. So because G here is, of course, determinant of the metric, and that is also a properties of our space-time. So therefore, we say L is not directly coupling with R, which is representing the gravity, but indirectly through G. So that's why we call it minimal. But there are also now non-minimal coupling, or directly, which L and I mean the Maxwell Lagrangian and the Richter scalar, they directly get multiplied. So that is how we call it minimally coupled. Is it okay?
I see what you mean, but I don't think I see the motivation behind it.
Behind the minimally coupling, you mean?
Yes. Yes, sir.
Okay. First of all, if you make a non-minimal coupling, first thing, even in linear Maxwell theory, okay, I mean L equal X. The bad news is our Maxwell equation will be nonlinear, understood? Which we don't expect, actually. So that is how they first in the. I don't say you don't have to write the coupling non-minimally. Yes, you can do it, and that is another theory. But the theory we are working here, we say, okay, we have Maxwell theory, and we have gravity, they coupled, but in minimal form, such that the Maxwell theory will remain still linear. Understood? Maxwell equation is still linear. So the non-minimal coupling also you can search on literature, find many papers. But the thing is, as long as we are, the simplification that we are doing here, or in general, it was done from the beginning. If you notice the Riemann-Rosen solution, the term which involves the mass, which is creating, actually that is the source of gravity, and the term which creates charge, I mean charge is there, they are completely separated. So if you switch off one of them, the other will still be there. So this is how we say they are minimally coupled. Anyway, let me go on. And then we have here X and Y. They are, as I said, Maxwell invariant. I just introduced them here. So what is our task now is to variate it. As I said, variation of the action, if the Maxwell term or the nonlinear Maxwell term is not there, everybody knows it will end up with Einstein equation without source. So then this is the first part. So I even though I wrote the detail here for if anybody is not familiar. But the second part, which is the additional part, now I'm going to put a little bit time on it. So we have matter field here, L, and L gives you the energy momentum tensor. I don't go line by line the detail because this lecture note, I think, will be available in the system. So later on you can get it. But the thing is, when you go on and use all the skills in variation, what happens to energy momentum tensor? Up to here, we still didn't put the explicit form of L. It's just a general matter source. But if you try to find these energy momentum tensor based on the definition of X and Y, and of course the Lagrangian L, it comes, as you see here, all details are written here, and I'm not going to go line by line because these are very obvious, but for the record, I put them all here. And the thing is, you just go on, you will see that at the end, as I said, the procedure is a little bit long, but then you come to a very beautiful result. So T mono, as I said, the Einstein equation, G mono equal kappa T mono. Kappa here is actually 8 pi G over C to the power 4. Everybody knows this is the coupling constant to match two sides, but we put C equal 1. This is the, but not G. This is the convention. Usually gravities they make. So I also use C equal 1, but G is still there. So now T mono, as you can see here, this is what I observed in some papers. The new researcher, they make mistake. So now we have T mono equal to L minus Y, Ly, and these are multiplied by G mono minus Lx, and here we have F nu lambda. So this is the explicit form, and this is the proof you can follow yourself. Now here, if you put linear Maxwell theory, so we will have exactly the energy momentum tensor of Maxwell's Lagrangian, which everybody, I'm sure, is familiar in this room. So now we have Einstein equation with T mono, which is depending on the derivative of Lagrangian with respect to X and Y, which X and Y are, as you know, the Maxwell invariants. So now you may ask here the question, L, X, and Y, we didn't put any condition on it. What kind of function it could be? It can be anything, whatever we want. Of course, there are some constraints we should consider, and I will give you later, but at least it should be differentiable with respect to X and Y, and of course continuous. So because Maxwell's linear theory also, it is continuous and differentiable. Anyway, so now after we found Einstein equation, we have to look at Maxwell equation also. Even here, I saw mistakes in literature. So for the same reason, I gave the full proof of what will be the Maxwell equation here. So we know that even we can start from flat space, Minkowski space, find the equation, and then by just changing partial with covariant derivative, we promote it to curve. This is what I do here. So first we start from Minkowski space, and then we use the Euler-Lagrange equation, and then we go on. So again, line by line, I don't give these calculation. I'm sure if you wish, you can find them later. But the thing is, they are not straightforward. You have to follow, and then you find the answer here. So now we have our equation. Actually, we can call it Maxwell, nonlinear Maxwell equation is given here. So this is in Minkowski space. So when you take Lx to be -1 and Ly 0, it comes exactly Maxwell equation, special theory of relativity. I mean, in Minkowski space-time, but when we come to curved space, we change our ordinary derivative with covariant derivative. So now this is our equation. Of course, here we didn't consider, we are in our source of electromagnetic field or somewhere else, so that's why there is no source. So J is 0, that's why in the right side we have 0. So these equations, of course, they give, yes?
Sorry, one question which may be actually irrelevant, but do we assume any discrete symmetries in the system or in the model?
Not yet.
Okay. Okay, thank you.
Okay, the point is, again, we go back, we remember that Maxwell's equation, actually Maxwell linear theory, we had 4 Maxwell equations, but 2 of them they come as Bianchi identity, I think you know, and the other two we call them Maxwell equations. So Bianchi identity also we have here, which means directly I wrote somewhere else, but anyway, covariant derivative of rho f mu nu to be 0, and then this is the Maxwell equation. So together they will handle our problem. Now what we found Einstein equation. Actually, we better call it Einstein nonlinear Maxwell equation. G mu nu equal K T mu nu. What is T mu nu? T mu nu depends on our Lagrangian nonlinear Lagrangian, and it's the partial derivative with respect to x and y, which they are Maxwell inverse. And I have to also add time. Okay. And then on the other hand, we have Maxwell equation here. Plus, we have also Bianchi identity, which should be all together handling our system. So now, as I already said, when L equal minus x, which means we are in linear Maxwell theory, we will get everything perfectly in accordance with Maxwell theory. Okay, now here I'm going to introduce the metric, as you said, Mr. Sonner. So the metric here, my aim, of course, it can be anything. You can start from spherically, cylindrically, axially symmetric, even rotational. But here I am trying to find a solution for a particle with charge. So then it means that we are talking about a static, spherically symmetric solution for our space-time, while our particle or our central object may have charge, electric charge, and magnetic charge both, monopole. So that's why I started from very perfectly symmetric, spherically symmetric solution. Actually, when I say perfectly, yeah, we have to start from a second function f here, but since at the end I knew they are going to be equal due to the Einstein equation, from the beginning I started with f and f. So GTT and GRR, they are inverse of each other. So, but anyway, but what we see here, I have considered our f or Maxwell field, or let's say electromagnetic field, to be the radial electric and the radial magnetic field. So as I said, we consider the particle which we are working on, its the space-time in this neighborhood, it has magnetic and electric monopole both. So that's why we consider the field to be radially outward. Anyway, so we remember f mu nu, if you recall, f mu nu tensor, and also its dual. So how we find its dual, the definition of dual field I already gave at the beginning. So you just apply, you will find its f mu nu star dual here, or you can use also exterior formalism. I don't know whether you are familiar or not in differential geometry. That may be even easier. So you just here, as you see, f is in exterior form. So just take its dual using the technique over, and you get exactly the thing. It's here, written here. So, but they are equivalent with the metrics I wrote.
Habib Hocam, Habib Hocam, don't you have 1 over square root of minus g in the F dual?
Excuse me?
Don't you have 1 over root square minus g, like determinant of the metric in the F tilde? In your definition, I remember it.
Fs star, you mean? No, this is the final answer.
Yes, sir.
Understood?
Yeah, I thought in its definition there was like dependence on the
determinant. No, there was,
of
course there was, but the thing is, after that square root of minus g was considered, these are the answers.
Oh, it was already included, you say?
Yes, because that f mu nu was f mu nu up, if you remember.
Oh, okay. Okay, sure. Thank you. Thank you.
Okay. So we come here, I'm going to find x and y explicitly because I have f mu nu and f mu nu star. These are not difficult. And the thing is, we get exactly as we expected. X is equal half b square minus e square, which is the energy density. Like what we know from Maxwell theory, and y is also. And then the Maxwell equation we apply. together with Bianchi identity. Maxwell equation, after you just write the covariant derivative into normal, we need this square root of minus g here, and then we just expand it, and then overall this will be the equation ELX minus BLY equal constant over R squared. Just I emphasize that I didn't specify any L. It's still completely general. So now the Bianchi identity also should be satisfied. Again, by just canceling, opening, you find out from Bianchi identity, B should be QM over R squared. So which is exactly the magnetic field of a magnetic monopole. But when you consider this B into our Maxwell equation, we will have a new equation depending on Lx and Ly, which E will be found from there. So E seems to be more complicated than magnetic field. And T mono, of course, we already found. Now I just apply or let's say I plug into T mono to find different component of energy momentum tensor. This is what I do here. I did it actually. So we have T00, we have T11. Actually, this is a mixed form of T mono, directly gives us the energy density and the pressure in different directions. So then, without going through the detail, I give you the final result. So all details are written here. If you wish, you can have access. So T00 specifically and T11 are the same. And that is exactly why GTT and GRR would give you F of R equal to, GTT and GRR to be inverse of each other. This is why I have considered from the beginning. So T00 and T11 equal, T22 and T33 also equal. And as you can see, we found them. But to solve Einstein field equation, we don't need to solve them all, because actually from here it is clear we have two equations left. One is in R and T direction, one is in theta and phi, but due to the integrability of Einstein theory, if you solve one of the equation, it satisfies the other as well. So that's why G00 equal K kappa, actually T00, I solve it. And that is how we find, by just considering F to be equal to 1 minus 2m over 2gm over R, like Schwarzschild form, but m is a function of R. Einstein equation becomes so simple as m prime equal to k over 2g R squared rho, which rho is the energy density, and energy density is nothing but minus T00. So T00 also we already found here. So then it means that we have T00, we have then rho, and then we put here and find m. So m will be k over 2g integral rho R squared dr plus m0. This is the general, complete general solution. And I didn't specify any Lagrangian for the theory. So now, of course, for when we put our L down, then we can find electric field, and then X and Y explicitly will be found. And finally, we will find what is rho, and then its integral gives us M. And by putting inside the metric function, we find F. So this is the story. Actually, practically up to here is everything is over. But now we're going to have kind of example. So the example which I'm going to give you is Born-Infeld theory itself, the one Born-Infeld introduced in 1934. So the Lagrangian for, actually the first I gave here is a linear Maxwell theory, and then I gave Born-Infeld. So in a summary, I gave all the equations we found together with the final equation here. And then for the linear Maxwell theory, L is minus 1 over 4 pi x. And then rho is equal to x plus E squared over 4 pi. I just used the equation I found. And then finally, E also became QE over R squared. And rho became 1 over 2 QM squared plus QE squared over 4 pi R squared after you put inside that M prime equation. we find M to be equal to what you see here. And after we put inside F, we find exactly the Risen-Nordstrom black hole solution. So this is just, it shows that our recipe works perfectly. Now for Born-Infeld theory. Born-Infeld theory is rather more nonlinear, as you can see. So B is Born-Infeld parameter. Actually, Born-Infeld, they put this B at the beginning for no reason, but they knew that when you put B to infinity, then you get Maxwell theory. When you take X and Y going to 0, again, you will get Maxwell. So in big field limit, you get also Maxwell theory. So when B goes to 0, Born-Infeld goes to 0 as well, which means we have vacuum. So these are the two different.
I actually have a question.
Yes.
Can I ask it now? Oh, so you said in the weak field limit it goes to the Maxwell theory, but
yes,
I mean
they should go.
But I think it should also include something like a theta term coming from, you know, wouldn't we also have a theta term? Not just a pure Maxwell theory, but because, you know, considering, I mean, the definition of the Y term, it's the field tensor times the Hodge dual. So it's kind of like the theta term. Am I mistaken? Or?
Actually, to be honest,
but
I don't hear very well your voice. But we can talk later about this issue because my time is getting over.
Okay.
Let me go and then we can talk on our other platform. But
Habib Hocam,
then
by the way,
I can see your question. But the thing is, in weak field limit, okay, generally in weak field, yes.
By the way, there is no speaker after you, so please don't get pressured. Like you may extend your time as you wish.
Okay,
like we are the last
thank
speaker,
you very
so
much.
there's no problem. Like we have usually like a discussion hour after this, but it's free discussion, so you can take your time however you like.
Okay, I wish you told me before because I escaped many of these.
Oh, I'm so sorry. Yeah.
But anyway, it is okay.
So
it is okay. Okay. It is okay. Thank you very much. We can discuss the issue.
Sorry, my apologies.
I have other things I didn't include it because I thought my time is just 1 hour. So, but I will
it's just 1 hour, but it's fine if you want to extend it. That's
okay, thank you very much.
Thank you.
But anyway, as I said, and our friend also mentioned, in weak field limit, this is one of the strong constraints on any nonlinear theory. They should go into Maxwell. They should coincide with Maxwell theory. So now here, of course, as I said, in B going to infinity, we get also Maxwell Lagrangian. And when B goes to 0, we get vacuum. So, and of course, Q also 0. Now, when we write Maxwell's nonlinear equation with B given as we knew Qm over R squared, you find Lx, Ly, and put it down. They are very, very long calculation, but magically they cancel each other, and then all of a sudden E comes out to be very simple. You see. I would like everybody, if you didn't do this calculation before, you do it once to see how perfectly Born and Infeld pick their terms in this nonlinear theory that the final form for electric field became so beautiful, as you can see here. So now what happens? Our electric field became, you see, because of these R0, which is a term depending on that constant you remember from the beginning we had, and also Qm, and these Born-Infeld parameter, E is not going to infinity at R0. You see, the maximum value for E is QE over R0 to the power 2. So that is actually the maximum electric field, and that is how they could, you know, put bound on the electric field of our charge. So now I already said what is R0 to the power 4 here, and then this C also by 4 pi, we call it QE. They may not be directly the charge or electric or magnetic charge, but they are related. So with some constant. So anyway, R0, which is the square root of Q is Qm square plus QE square root, is just a characteristic length. for particle solution coming out from Born-Infeld theory, they call it, this is the radius of the particle. So that is just an interpretation. I mean, no proof for that. You can interpret it something else. But in general, that is R0. It shows how strong or how large your maximum field, electric field could be. So now, then after we found the electric field and magnetic field, it means we have our T-mono, I mean T00, and T00, although it looks to be complicated, but after you put everything down, it becomes so simple. You can see that how simple is the energy density. And by the way, one of the strong condition on L is rho should be positive, because rho is going to be the energy density. So then when you propose any nonlinear Lagrangian, you have to keep in your mind your energy density should be positive. Actually, after we found rho, you can put inside the master equation, master Einstein equation, and find M. Actually, this is the solution. So M of R is equal to minus B square over 3R cubed plus B square 1 elliptic integral we have here plus M0. So of course, this integral is not in terms of basic functions. But anyway, one can find it by just some hanky-panky change of variable. So after you do that, I wrote how to do it. You can find the total, the solution for M to be a constant, which we call it M0 now. But this M0 is not supposed to be the Schwarzschild mass. So that is a constant, but it is related to Schwarzschild mass, plus few terms depending on B, R0, and the other parameter, let's say QM and QE. So the full solution for metric in Born-Infeld theory is found here, as you see. If you do not put M00, so some authors, they say, okay, M0 is the central, let's say, mass, the mass of the central object. If we make it 0, we will have all the energy, all the contribution through the electromagnetic. So even if there is a term proportional to 1 over R, that will be the electromagnetic mass of the system. So then in such case, you can create particle model. So then you have to adjust M0, your, let's say, constant term, in a way that at R0, the solution become regular. So there are papers, they try to find regular solution from Born-Infeld theory, but there is a problem here. Actually, the problem I didn't mention here, I do here because I feel I have time because of what happens. As I said from the beginning, Lagrangian, which we used here, Born-Infeld, is the first one, but they knew from the very beginning they have proposed that Lagrangian. So they could propose any other form of Lagrangian. So which one would be the correct one? And which one would be the most advantageous one? So that is very interesting question. And even now, nobody knows the answer. But the thing is, there are some theorems. If you are looking for a regular black hole solution, let's say, so your Lagrangian shouldn't have, especially if it is purely electric, it shouldn't have Maxwell limit. So if you have a Lagrangian which is big field limit to Maxwell theory, your black hole wouldn't be regular. However, if you have a purely magnetic black hole, which means your source of energy or source of, let's say, electromagnetic field is only a magnetic charge, that is possible. Therefore, you may have the Maxwell limit and also your black hole may be regular. So that is very interesting theorem. The theorem is published in Physics Review letter. So I didn't cite it here. But the other things which I already asked, what could be other condition on L? So physical admissibility, we call it. I mean, can we say anything, any L is welcome? Actually, there are some minimum requirements that L should satisfy. The first thing is it should be single branch and continuous and differentiable. I already said. These are the basic properties even the Maxwell's linear theory satisfy. How about other? In Maxwell linear theory, there is no the second invariant, Maxwell invariant. I mean, Y is not involved. And we know that for parity invariance, X is already parity under parity invariance, but Y is not due to existence of E and B together. So then L should be anti-symmetry. Actually, it is symmetry with respect to, we call it, it should be even with respect to Y. So that is due to the parity invariance. So some of the authors, they decided to consider Lxy not to be a function of Lx and Y, but Lx and Y square. So even in Born-Infeld theory, if you notice, Y appeared as Y square. That is exactly due to parity invariance. And also, I already said rho or the energy density should be positive. So then it gives rho positive gives this condition to be satisfied, which after you just find out what is E square in terms of X and Y, the condition reduces to a very beautiful condition in terms of L, its partial derivatives, and X and Y here it's written. So these are the minimum requirement L should satisfy in order to be at least acceptable to be considered as a new model. But there are other symmetries which Maxwell theory already carries, and we expect not strongly, but in some extension that our new model also they admit. For example, we know that our Maxwell action or Maxwell linear action is invariant under conformal transformation. So conformal transformation means that if you multiply your G mu nu or metric tensor by a constant, sorry, by a function of our coordinates, then of course X also transforms and G also transforms, and you can see that a square root of minus G times X doesn't change. So it means that our action is, and if there is no source, because when there is source, the source term will not be invariant. Without source, our Maxwell equation also is conformally invariant. So we expect that Lagrangian, which you introduce, I said these are not restricted, but that could be better to be, to satisfy this symmetry. And there is another Hughes dual transformation, which means actually when you rotate your fields or you introduce your new field in terms of the rotation of our old fields, if the old field they satisfy Maxwell equation, the new field also. So in nonlinear theory also we expect this. This is called Hughes dual transformation, and that is Hughes dual symmetry to be held by our new theory as well. So if you consider these two symmetry only, which Maxwell theory carries, we come across a very specific Lagrangian here. So this Lagrangian, which is minus x cosine gamma plus cosine gamma square root of x squared plus y squared, is the one which gives maximum symmetry among the nonlinear Lagrangian for electromagnetic theory. So there are papers written based on this Lagrangian. I cited, I think I gave some reference at the end, but this is the most feasible, let's say, so far, in addition to Born-Infeld theory, Lagrangian, which one can work out. And now there are other conditions, such as we know that causality and unitary principles, they put some condition. I didn't go through the detail, They are all published in literature, you can find them. But just as a summary, if you're going to consider causality principle satisfied together with unitarity, then we have to consider also these few conditions also to be satisfied. So the good thing is Born-Feld theory satisfies these conditions. And also the other model I already introduced, the maximum symmetric model also satisfies, of course, up to certain gamma. So I stopped here because I thought this much will be the case, but now I just add because it seems that I have a little bit more time. The problem is, as I said, okay, we have many models. I would add them, I mean, explicitly on this lecture if I knew that I would reach them. We have many models you can search on literature, which some of them are purely electric, some of them are purely magnetic. And also we have regular black hole solutions based on some pure electric Lagrangian. When they are pure electric, I said they don't have Maxwell limit, and that means that the black hole solution doesn't have Maxwell limit, Rising-Nordström limit. But the other one, when it is a magnetic solution, as I said, according to the theorem proved by Brunnikov, they can have Maxwell limit, which means in a certain limit they go to Maxwell Rising-Nordström solution, but they are still regular. So the structure of black holes, they are after we add nonlinear electrodynamic Lagrangian coupled to gravity minimally, it became richer. So when you write down the geodesic equation, I don't know the other thermodynamic properties, let's say even thermodynamic stability, even dynamic stability of black hole, they all are affected by these parameters, which we call it nonlinear parameter of the theory. So therefore, adding nonlinear electrodynamic coupled to gravity makes the whole system more richer. But one thing we should keep in our mind, because nowadays, since the subjects for doing research, especially for elementary researchers, they became almost, let's say, invisible. So what they do, they create subjects for research, and one of them making the already linearly theory to nonlinear. So I don't criticize any of them. They may be correct or not. I mean, up to certain extension, they may be correct. But the nonlinear theory we discussed today is not a new nonlinear. It is almost 90, 80 years old age. So it's from 1934, and that is very old question. So it's not just to fill a gap for doing research. It has application, as I said. It makes it answers some questions which even from high school we had in our mind. So in general, this nonlinear theory, I mean non-dynamic theory, is not just an exotic theory which comes and goes. I think it will remain, especially due to its application in string theory. I see very bright future for these theories. I thank you very much. I think my time is over. So I managed exactly 1 hour to finish. So my 1 hour is over. So thank you very much. And I am here to answer any question if there is.
Thank you. Thank you so much, Habib Hocam. Firstly, that was a beautiful talk. Thank you so much. Secondly, I would like to apologize for not informing you earlier that you are the last speaker. So, well, yeah, we have this free discussion now at the very end each day to, stimulate some brainstorming together without any formal topic. But so you could have used that time. I should have told you this earlier. My bad. Actually, let me ask the audience if anyone has any question. Okay, then let's thank our speaker again. Thank you so much.
I thank you very much.
There was a question about the theta term, but I believe
I actually have a question, but
yeah.
okay. But I think
Habib Hoca is going to stay for the discussion hour, or is he going to leave?
Yeah, so let me just then get all the quick questions. Then let me end recording, then we can chat a little bit about longer things.
Soner, I have a very quick comment.
Yes, please.
Yes, please.
Hocam, please share your lecture notes with us as soon as possible, because I found it very interesting. We are also working on that, and it will be very helpful for us.
Definitely, it's my pleasure. I will send to Mr. Suner that he can add to the platform.
Yeah,
Habib
okay.
Hocam, don't share it. Let them work in dark. Okay, then.
Maybe another quick comment. I'm not sure if you have seen those papers, but with a non-minimal coupling, that problem of finding a regular black hole solution, it was solved very recently. It's called electromagnetic quasi-topological gravity. Have you seen those papers?
Actually, I think I saw it, but I didn't go through the detail. These days we were a little bit busy, but thank you very much for reminding. I will check it carefully. Thank you.
And well, as far as I can see here, you have all the tools, so you can very easily extend this work for theories with non-minimal coupling. And well, I haven't studied those papers in a detailed extent, but it seems they have some very interesting results there too.
You are very much right. Actually, the thing I gave here, as I said from the beginning, my aim was to give a compact lecture note, including everything one needs to start doing research in non-electrodynamic coupled with gravity. So, of course, minimally. So I think it's ready to be used for everybody. And I also use it. And my students also here, we use together. Yes, thank you for your comment.
Thanks a lot.
Okay, thanks a lot. I'm stopping the recording.